So hi everyone. Thank you very much for attending this presentation. My name is Katell Lagatu, and I'm going to present you my PhD, which is entitled Actuator Fault Recovery Control Strategy with Deep Reinforcement Learning, Application to Unmanned Underwater Vehicles. So let's start with a little bit of context. My PhD is a Naval Group CIFRE Defense PhD with ENSTA Bretagne in Katell with Flinders University. So I spent the 6 first months of my PhD in Naval Group at Oriol. Then I spent 1 year and a half in Australia at Flinders University. And I finished my PhD for the last year in Brest at ENSTA Bretagne. And I will officially end my PhD at the beginning of next month. So for this presentation, I will start by giving a small overview of the general problem. Then I will briefly talk about the state of the art, which will lead to the result statements. Then I will explain my proposed approach that will be tested on an application case. And I will finish by showing you some of the results that we obtained, both in simulation and in real world. So first, let's start with the general problem. So we consider in my PhD autonomous dynamic systems controlled by model-based controller. We can see here a classical closed-loop control with a controller relying on the feedback from the system dynamics to perform the desired motion. The model-based controller is based on this classical evolution equation, with f the evolution function of the system, which is known during the nominal condition. But in the presence of an unwanted change in the system model, namely a fault, the evolution equation becomes this one. So this changes because the fault affects the model of the system. And instead of having the function f known, we have a new f prime function, which is unknown. The challenge here is that there is a difference between the model used by the controller, relying on f, and the real model of the faulty planes, which relies on f prime, that we don't know. This can lead to the risk of the mission failure of the system, or in the worst case, the loss of the system. So there are different types of faults that can occur in autonomous dynamic systems, for example, software faults or sensor faults. But in my PhD, we focus only on actuator faults. They can be partial, for example, a loss of efficiency of one actuator, or it can also be total faults with like a total failure or breakdown. We make a few assumptions to start with in my PhD. The first one is, as we focus only on actuator faults, we will assume that there is no other disturbances, so no other fault and no external disturbances like marine currents or wind or anything. We also assume that the faulty system remains controllable, which means that the system has enough other actuators to be able to move in the desired direction despite the fault. The objective of my PhD is then to develop a strategy to overcome actuator faults. This leads us to explore fault-tolerant controllers, which are controllers designed to recover from faults. The goal of fault-tolerant controllers is to address some key characteristics. The first one is optimal recovery performance, which is how well the system can perform despite the fault. There is also stability of the closed-loop control, which is essential. There is also the adaptability to various fault scenarios, the generalizability to unexpected faults, and also the last one is resource efficiency, which is very important because fault-tolerant control is often embedded in physical platforms with limited resources. So all these key characteristics define the overall performance of a fault-tolerant controller. And now let's see what already exists in the literature. There are two main categories of fault-tolerant control, model-based controllers and machine learning-based controllers. Among the model-based controllers, we can find the robust passive control, but the most commonly used is adaptive control using explicit fault diagnosis, or EFD. In this method, the controller parameters vary according to the fault information. Among the machine learning controllers, the most used method is end-to-end deep reinforcement learning. So now we'll see a bit in detail what these two main methods mean. First, what is adaptive control using fault diagnosis? The first step of this approach is to obtain the fault diagnosis. This includes obtaining isolation, so the information of which actuator is faulty, and identification, which is obtaining the information of the extent of the fault. So for example, it can be the coefficient modeling the loss of efficiency of one actuator. So it's important to note that EFD can be based on prior knowledge about the system model and the fault, or it can also be based on online estimation. So this means that it can be also estimated during the mission. Once the EFD is obtained, a control relocation is performed based on EFD. So before talking about control relocation, let's first understand what is control allocation. So classically, in a controller, we have two different blocks. The first block is the control law, which takes as an input the observation from the system and which outputs the desired forces and torques, tau. And then the second block is control allocation, which converts the desired forces tau into actuator inputs U. And this is done through the control allocation matrix, H. So now that we said that, the control reallocation is about adjusting the H matrix based on EFD. So this means performing a redistribution of the forces among the actuators. So basically, control reallocation is about answering the question, if one actuator is faulty, how to use the other actuators to keep performing the desired movement despite the fault. So now that we said that, So now to understand the second type of existing method, we need to see first some key elements about what is reinforcement learning. So this involves an agent trained in an environment through trial and error. At each step of the training, the agent will take one action and will have from the environment a new state and reward. This is all done in the framework of a Markov decision process. And the goal of the agent is to learn a policy of action which maximizes the long-term cumulative rewards. Basically, at the start of the training, the agents will take random actions because it will not be trained at all and will not reach the objective of the mission. Then, after a while, the agent will be able to take more meaningful actions because it will have updated its policy of action. So for example, it will be able to reach the waypoints, but not in an optimal way. And then if the training is efficient, at the end of the training, the agent will be able to reach the waypoints in an optimal way because it will have been find a policy of action which is optimal and which maximizes the cumulative reward. So now, what is deep reinforcement learning? So reinforcement learning struggles with high-dimensional and continuous spaces. This is why it's very common to use neural networks to approximate policies. The combination of neural network and reinforcement learning form deep reinforcement learning, or DRL. So you can see here on the scheme that the policy of the agent is replaced by neural networks. So neural networks are powerful tools because it can approximate complex functions and learn complex policies during training, and it's also able to adapt to numerous different situations encountered during training. So now to come back to our context, the goal of the DRL agent is to improve the system performance in case of actuator faults. And when I was talking about end-to-end DRL, I meant a DRL method where the action is directly the actuator inputs. So the controller is only made of DRL. So this is a purely machine learning controller. So now that we saw what existing methods consist in, let's see their limits. For the model-based controllers, the main limit is obtaining an EFD can be very challenging. So especially when there are numerous actuator faults and when there is a complex geometry of the actuators. This type of methods can lack adaptability and also resource efficiency. Regarding the machine learning controllers, the main limit is the controller transparency, because neural networks are made of interlocked nonlinear functions, so the stability is very hard to guarantee. We often use the image of a black box of which we can't guarantee or predict the outputs. So this is why in my PhD, I made the choice of using a hybrid controller with both the advantages of model-based control and machine learning-based control to have both the adaptability and stability. This leads us to the reader statement, which is the combination of DRL and model-based control improves the overall performance of an autonomous dynamic system subject to actuator faults compared to async methods. The main contribution in my PhD is the development of an adaptive model-based controller using DRL to adjust the control allocation matrix based only on observing the system's behavior. So for the DRL part, the goal for the agents will be to learn how to adjust the allocation matrix, so to perform a control reallocation based on the observation of the planes. So this will allow to have the adaptability of the DRL, and also this allows to bypass the need for fault diagnosis. So why is that? It's because the agent will only rely on the observation of the behavior of the system. So basically position, orientation, and velocities. The agent will not have any access or any need for the fault information. So it will not need to know which actuator is faulty or the extent of the fault. It just needs to observe the planes. And we will integrate this control allocation based on DRL to a model-based controller. So I will show you a bit later how it is done. And this will bring a certain stability. So before entering a bit more into the details of the proposed approach, we must answer the question, in which cases using DRL? So we want to use DRL only when an abnormal behavior is observed. So as we can see on this small scheme, when there is no fault, we want to use only the model-based control. And when a fault is detected, we will use our hybrid control using DRL and model-based control. So we want to do that because it enables to maintain an optimal control in nominal situations, because we don't need to add the uncertainty linked to the DRL when we don't need it, when there is no fault. And also because it can reduce the number of scenarios that the DRL is supposed to learn during the training. So it's not supposed to learn the nominal conditions. The detection threshold is defined and depends on the considered system. And it's important to note that it is very different from a diagnosis. We are not performing a diagnosis here. We just need a binary indicator saying if there is a problem in the system or not. So it's just about observing the behavior of the system. So here is the structure of the proposed hybrid controller. We have a reference vector, which includes the desired movements, then a model-based controller, which integrates the control reallocation process. The control reallocation process is performed thanks to a trained DRL model that was trained in simulation. And we also add a post-processing step. The system dynamics outputs an observation, which will serve for the closed-loop control. So it will come back to the model-based controller, and will also serve as the input of the trained DRL model. So first, let's see how to adjust the allocation matrix thanks to a DRL-based method. So the goal is to reallocate the forces among the system's actuators using DRL. So for this, we will add some weights, namely W, to the coefficients of the control allocation matrix. So the vector of the desired forces F will be converted into actuator inputs through a control allocation matrix adjusted with DRL. So basically, the weights, which are the outputs of the DRL model, will redistribute the forces among the remaining actuators. So now that we saw how to adjust the control allocation matrix, I will show you how to train our DRL agents. For the training, we will use an environment, which can be, for example, an underwater world, or for example, an aerial environment. the agent will be, for example, an underwater vehicle or like any kind of vehicle which can be subject to actuator faults. The agents will have sensors on it, and this will be the observation vector of the DRL process. So the observation will be including the position, orientation, and velocities of the agents. From this observation, the agent will take actions that will be the weight that we just saw earlier. And to take the best action, during its training, the agent will rely on the feedback from the environment, so the reward. And the reward wants to minimize the difference between observed and desired behavior. So it will look for minimizing the error. And we can notice here that there is still no need for fault diagnosis, as the agent only relies on the observation of the system. During the training, to have a more efficient training, we will apply domain randomization, which is about exposing the DRL agent to various actuator faults in order to improve its adaptability. So at each episode, so an episode is a sequence of interactions from a starting point to an ending point. So at each episode, a fault is randomly applied to the system. We also add a post-processing step in order to limit abrupt variations in the control allocation matrix values. So for this, we will use a low-pass filter. So now we saw how to adjust the allocation matrix and how to train our DRL agents, which will produce the weights W. And now we will see how to integrate this control allocation process into the model-based controller. So in order to ensure the stability of the closed-loop system, the control allocation matrix H must be included in the controller gain computation. For this, the controller gain, that we note K here, will be computed not only in function of the classical matrices A and B, which are the state and input matrices, but also in function of the control allocation matrix that we integrate in the equation. And this control allocation matrix is adjusted by the DRL. So basically, the gain K is calculated to ensure stability, and it will be a local stability because it will be recomputed at each time step. We can see here a summary of the whole process. At each time step, the DRL model will receive from the system an observation and will produce an action, which are the weights. The weights will adjust the control allocation matrix integrated in the computation of the gain K. And this gain K will be used to compute the actuator inputs of the system. So it's interesting to note here that contrary to classical control, where there are two blocks, one block for control law and one block for control allocation, here we have only one big block because we integrated the control allocation process into the control law. So this means that there is only one block which outputs directly the actuator's inputs. So there are several advantages of this proposed hybrid controller. First, as we use DRL to perform control allocation, we can bypass the need for fault diagnosis. There is also the advantage of using the adaptability and generalizability ability of DRL, which are very essential for various fault scenarios. And also, once trained, the DRL model is quite efficient for the computation power. Also, we integrated the control allocation process into the model-based controller framework, which could guarantee a local stability at each time step. And as we added a post-processing step, we could approach global stability because we reduced the variations of the control allocation matrix. So all of these advantages suggest an improvement of the overall performance of an autonomous dynamic system subject to actuator faults compared to everything methods. And now we need to test this method on an application case. The application case that we choose here is autonomous underwater vehicle and thruster faults. We chose the BlueROV2 Heavy for the autonomous underwater vehicle, which is an AUV which has 8 thrusters and which can be used in defense applications, for example, mine detection or covering area or reconnaissance. So here we can see the actuator configuration of the BlueROV2 Heavy. So it has 8 thrusters, 4 horizontal and 4 vertical. In my PhD, the focus is on the 4 horizontal thrusters that we name T0, T1, T2, and T3, and which control X, Y, and yaw directions. So let's consider this fault scenario. We have this AUV following a straight line trajectory along the x-axis with no other disturbances, so no wind and no currents. An actuator fault occurs during the mission, which leads to translation errors and rotation error along the y and yaw directions. And the objective is to minimize these unwanted deviations along the y and yaw axis caused by thruster faults. To apply the proposed approach to the BlueROV, we need to make some technical choices. The first one is the choice of the model-based controller. We chose for this the linear quadratic control, or LQR controller, because this is standard controller for linear systems, and the stability is quite straightforward to guarantee. For the choice of the DRL algorithm, we chose the soft actor critic, and we validated this choice in a first article for a conference. For this application case, we added a working hypothesis. We assumed that the state of the AUV, so position and velocity, is known, because as we focus on control, we assume that the navigation part is okay. Now, for applying the proposed approach, as we focus on a scenario where we only follow the x-axis, we will consider only the first line of the control allocation matrix, which is associated with the x-axis. So the DRL model will output only 4 weights W. And the weights, yeah, so the output, of the DRL model trained in simulation. Now, in order to apply the proposed approach, a DRL training has to be carried out on the BlueROV2 Heavy. The issue that arose in my PhD is that training DRL models directly on physical AUVs is very impractical due to time, energy, operational costs involved, and there are also potential risks and material damage, and so on. So for all of these reasons, the training must be carried out in simulation. For this, I created an environment for the training using open access tools for fault conditions. And this was the topic of a second paper that I presented at the Oceans Conference. So this is the training environment that I created for the DRL agents. So to train the DRL agent, I used a Docker container, and inside of it, there is the world simulation. I used the gazebo simulator for the simulation of the underwater world with the plugin UUV simulator that uses ROS. For the BlueROV2 Heavy, I used a model of its dynamics. Now, to do the bridge between the world simulation and the DRL environment, I used OpenAI ROS Bridge, which allows to use RL through ROS nodes. So basically, the actions of the DRL model will be the inputs of the BlueROV, and the observations needed for the DRL training will come from the sensors of the BlueROV. For the DRL environment, all that is reward definition and the observation and action space definition will be in an environment called OpenAI Gym, which is very common. And I also used a bank of algorithms, which is named Stable Baseline, so which includes several RL algorithms. And the chosen algorithm, so soft actor critic, will directly influence the controller, as we saw earlier. So the controller which controls the BlueROV. So now let's see the training of the DRL model, but this time applied to the BlueROV2 Heavy. So the environment is the underwater world of the BlueROV2 Heavy. The agent is the BlueROV2 Heavy. Its observation comes from its sensors and will include the Y and the yaw, because that's the direction impacted by the fault. This observation will serve to take actions. The action will be the 4 weights. to adjust the control allocation matrix. And to take the best action possible, during the training, the agent will receive the reward to update its action policy. And the reward aims to minimize the errors along the Y and U axis. So this is why we can see the expression of the reward at the end of the page. This is minus exponential of the errors along the Y and U axis. Regarding domain randomization, at each episode, when the training starts, a random thruster is selected and its efficiency is set at 0% or 10%. So we do this because we want to focus on the more severe fault cases, and we will assess the generalizability of the DRL to overcome the less severe fault cases. We can also see here the learning curve of the mean reward, and we can see that it could converge after around 40K. So it took approximately 7 hours to converge. I just want to show you what the training looks like. So at the beginning of the training, here we can see a small BlueROV evolving in the environment. It's supposed to follow a straight line, but here we can see that there is a big deviation because it's just taking random actions, so random weights, and it doesn't allocate well the forces. And here is at the end of the DRL training. So we can see that the DRL model could converge toward a policy which allows the BlueROV to follow a straight line despite the fault. Now that we have a trained DRL model, let's evaluate the proposed approach. So to do this, we compared the proposed approach to different other controllers. First one is a standard LQR controller to have a baseline for evaluating. Second one is a conventional gain-varying LQR controller. So the goal is to compare the proposed approach with another adaptive controller, but which doesn't use any DRL, in order to evaluate the advantage of using DRL. And the third one is the proposed approach that we will name in the following presentation LQR DRL. We also compared all of these controllers to non-model-based PID controllers. So I will not talk about it in this presentation because it would be too long. But this was the topic of the third paper that I could present in CIFRE in Atlanta. So now that I said that, so there are two evaluation steps. The first one is the evaluation of the controllers in simulation with UUV simulator to see how well the LQR DRL controller performs compared to the other controllers. And step two is the evaluation of all of these controllers in the physical, in the real world with a physical drone to see if we can apply directly our trained DRL model in simulation to the physical drone and how well it performs compared to the simulation. To measure the performance of all of these controllers in simulation and in real world, we will use these performance indices that are the integral of the errors, so the Y and U errors that are impacted by the fault. And we also added some statistical tests in order to evaluate the significance of the results. So here we can see the first simulation results. In this table, we can see the mean and standard deviation of the performance indices from 0% to 100% thruster efficiency for the three compared controllers. The best results are highlighted in green, second best in orange, and the other one are not highlighted. So we can see here that our LQR DRL controller outperformed the other controllers between 0% efficiency and 70% efficiency, with an error reduction up to 74% efficiency compared to a standard controller, and 40% efficiency compared to the adaptive controller. So this shows the generalizability of the DRL model because it could overcome not only the faults seen during the training, so with 0% and 10%, but also less severe faults that were not encountered during the training. So this is because of the neural network's ability. Beyond 70%, the LQR DRL is outperformed by the other controller, which makes sense because it's quite far away from what the DRL agents encountered during the training. We also performed statistical tests, and we computed the p-value, which is quite small, and extremely small, sorry, I mean, which means that there is a highly significance of the results. Before transferring the DRL model to the physical drone, we wanted to first transfer it to a different simulator in order to assess its ability to adapt to a different world with different dynamics and slightly different modeling of the drone to see if it's able to perform in a different environments. So for this, we used the new Naval Group Pacific simulator called LOTISIM. So the scenario that we'll see here is when thrust efficiency T0 is set at 10%. On the left, we can see the green flag, which is the waypoint that the BlueROV is supposed to reach. In red, we see the trajectory of the BlueROV when controlled by a standard controller, so when there is no DRL-based control relocation. And in blue, what is appearing at this moment, it's the trajectory of the BlueROV when controlled by our proposed controller, combining DRL and model-based control. And we can see that, contrary to the red trajectory, the blue one can follow a straight line, and finally it will reach the waypoint. So this means that the DRL model could be efficiently transferred to a different simulation environment and could efficiently perform the control relocation and overcome the fault. So now step 2 is experiments on a physical BlueROV. So for this, I used the test pool of Flinders University in Australia. For the localization, I used an underwater camera tracking an Aruco marker, as you can see in the picture. I evaluated different scenarios of faults with various efficiency levels of the 4 horizontal thrusters. I directly applied the DRL model to the physical BlueROV without any fine-tuning or anything, so it was directly applied. And all that is computing the input commands and the DRL model processing, it was done on a laptop, which was tethered to the physical BlueROV. So here is a first result that we obtained. So first, I will show you the case where we use a standard LQR controller, so with no control allocation. So it follows a straight line, then a fault happens, and we can see that there is a big deviation because there is no control relocation process. So it's just deviating and never recovering from the fault. And here we'll see the same scenario, but this time we will use our proposed approach. So a fault happens here. The behavior, an abnormal behavior is detected, so we use DRL. And this allows a relocation of forces to overcome the fault and follow a straight line. Here is another example where on the right we can see also the position of the BlueROV tracked by the camera. So first case, we use a standard controller, so there is no DRL-based control relocation. It's just standard, so we can see that there is a big deviation from the straight line. Yep. And second video, this time we'll use our proposed approach when an abnormal behavior is detected. And we can see that instead of deviating, it will keep following a straight line with a minimal error. We also have some numerical results obtained from the experiments. And we can see that our LQR DRL controller outperforms the other controllers in all the scenarios that we tested on the physical drone. We also performed statistical tests, and as in simulation, our p-values were extremely small. So this showed highly significance of the results. So all of the proposed approach and the experimental results were the topic of our last article that we submitted to a journal paper. So now let's conclude. So we have several thesis outcomes. First one is the development of a novel hybrid approach for overcoming actuator faults without any need for fault diagnosis. The advantages of the proposed approach is that we combine the adaptability of DRL with the stability of a model-based controller. We could validate this proposed approach in simulation and in real-world conditions. And we performed the comparison of the proposed approach with standard and adaptive existing strategies. The results showed that the hybrid controller outperformed the other evaluated controllers in reducing trajectory errors induced by actuator faults. And we show also the generalization ability of DRL because it could overcome faults that were not encountered during training, even with similar resisting behavior. So now for the research perspective, the first big point is towards realistic and challenging scenarios. We want to expand this work to a 6 degree of freedom trajectory tracking with more complex scenarios involving curve and longer scenarios. We also want to explore complex fault types, for example, nonlinear faults or time-varying faults and so on. An important point also is that we assume that there was no external disturbances, and now it would be great to add these external disturbances, so for example, marine currents in our case. And also we want to improve the transfer to the physical drone, for example, by adding some fine-tuning to have even better results, and also to be interesting to transfer our DRL model to another type of drone, for example, a torpedo-shaped AUV with fins faults. And finally, we also want to address DRL-based fault adaptation challenges. First one is that we like to have certain diagnoses to give to the operator. For example, we could perform reverse engineering based on the results of the DRL model. Also, we could improve DRL training, improving the training time and performance, and improving the realism of simulation environments with more modern tools. For example, training directly in the more modern simulator LotusSim. And here are the summary of the thesis contributions with the associated papers. And I think that's it for me. So thank you very much for your attention, and please don't hesitate if you have any question.
Merci, Katell. Thank you. Thank you. I found your presentation really excellent, with a lot of material and a lot of very convincing illustrations and dynamics of your slides. So that was really a good moment. So I thank you for in the name of everyone. We have, and also you left enough time for discussion, which is very good. Let me just, I haven't seen any hand raised or questions on the chat, so I will start. In fact, I first have a non-technical question, and then I have a technical question. My non-technical question is that you have you have new challenges. You showed that in your last slide, that there should be some continuation of the work. So does this mean that after your PhD defense, you will stay with Naval Group and go on with the work?
Yeah, ideally, I would love that. But for now, I'm not sure of what I will do. But there is already another PhD student working on these challenges, and who has already done a master internship on benchmarking DRL algorithms in different environments. And he will start his PhD soon. And his PhD will be about working on the following of my PhD and adding external disturbances and working in more realistic environments.
Okay, so it shows that Naval Group is really convinced and investing in this area. Okay, not so technical question, but still, you know, when I started working on neural networks many years ago, and we were also at that time I was in a research institute, and we were also trying to do some control with neural networks, and we were discussing with people from the traditional control systems world, les automaticiens, people in automatics. And when we started that, they really hated it.
Yes, I understand.
Because they say, we have good mathematics, we have proof for everything that we do, we have formulas, etc. We know what we do, And so what you're doing, you don't have any proof, don't have any, you cannot show that what you do is correct. And so they were not really convinced, and it took a lot of time to discuss that. So now time has passed, and I see that you have good results anyway, good comparison. But since we are talking about trustworthy AI in this kind of in this meeting, how can you convince the traditional control systems people that they can trust all this?
Yeah, so there are two things. First thing is that we only use our GL method when there is an abnormal behavior. So in nominal condition, we want to rely on optimal model-based control that don't use AI or anything. So we use AI only when it's totally necessary. And the second thing is that instead of using purely machine learning control, which was commonly done in the literature, we used an hybrid controller with model-based and AI. So we integrated our DRL method into the model-based control. So we have a stable framework, and this will be more, I hope, accepted by the automatician, because yeah, we really set boundaries to what the DRL can do, and it's definitely not a purely machine learning control. At the beginning of my PhD, I was working on purely machine learning control, so end-to-end DRL. So it was directly outputting the actuators command. But as a result, we saw that it was very, very unstable, and the outputs had very abrupt variations and made no physical sense. This is why we added this physical structure based on mathematical equations in order to improve this.
Yes, I think it's an important trend at the moment in AI to do some hybridation of language with more physical systems. Huh? Loic has a question. Loic, you can speak. I don't want to read your question, so please.
Yes, maybe just a question. Do you think about trying to estimate the error of your sensor during the training, even if you don't need them to make your control? Maybe taking it as an extended training information can help you maybe to train and also maybe to understand how the behavior in operation of your, because you maybe you will try to, detection is fault, or because its behavior it does not understand, etc. So did you think about it, or maybe it's something that you do not have time to try and but you let for later?
Yeah, exactly. So at the beginning of my PhD, I was looking at several articles talking about this, and several of them use so purely machine learning controllers, and they use also fault diagnosis. So during the training as well, and the observation vector of the DRL agents includes this fault diagnosis. So this is something that exists, and I think it's it's very good. We just wanted in my PhD to really bypass this need for fault diagnosis and look at the possibilities when we are in situations where fault diagnosis is difficult to obtain. So of course, when we have a system where there is directly, for example, a sensor on the actuators, and we can directly have the diagnosis, then we should use it, even during the training and during the mission. But we asked ourselves, what happens if we can't have any fault information, or even if there is just a deformation of the robot due to a collision, for example. So it's not easy to model this fault diagnosis. So how to translate this in a mathematical equation. So we really wanted to bypass this need for fault diagnosis and see what we can do without it. But it's just really possibility.
You do not want to use it as an input, but I say just as an external output to understand. It's just a supervised external information, not used as an input, but used as an observation of your behavior.
Okay, yeah. So you mean during training, DRL would
you only train it as an observation elements that maybe help you understand if it's something that is different from what has been seen, or maybe to have an explainability of your. But it's just right now. It's just a question. Thanks.
Yeah, no problem. It's a very good track. I think it's a very good lead for the future research. Definitely.
So I don't see any other hand raised, but I have another question before we close. And but please, if you want to speak, just raise your hand. I think that underwater vehicles are not the only ones, the only system that can benefit of this hybrid approach. Of course, what you have developed is, well, I think it's rather generic. The architecture, I would say, is generic, but maybe the implementation with the simulation and all the things that you have used may be a bit specific to the case that you were working on. So what effort would it need to adapt the whole system to a completely different system to be controlled?
Yeah, you're totally right, because for the proposed approach, I tried to stay in a very generic case, which can work on any system, any environment, and any kind of actuator force. But in practice, we had to really apply to BlueROV2 Heavy and make a lot of adjustments. So basically, what we would need to do is to identify trajectory patterns of the motion of the system. So it can be randomly selected during training. We need also to identify the potential faults, so we can apply them during training. And also for the action of the DRL, we need to identify which weights we need to learn for adjusting the controller action matrix. And of course, one of the biggest challenges is to have realistic training environments. So this is not very easy, because it's quite rare to have open access tools for this and realistic environments. So yeah, there are many things to change to apply to another vehicle. Yeah.
There's something also that can be changed, is that if you are not working in underwater framework, you can have fast communication between the system and external devices. And then you might also take advantage of fast communication for getting additional information or getting extra power for whatever you need to do, things like that you cannot do in underwater applications.
Yeah, definitely, yes. Yeah.
Milad, I think, Milad has a question.
Yes. Do you hear me?
Yes.
Yeah.
Thank you for the presentation. So just one question. You use the deep reinforcement learning to help the model-based approach to reach stability, if I well understood the presentation.
Yeah.
Yeah, to learn the weight. And what if you use the constraints from the model-based approach and integrate them in your reinforcement learning approach, in your loss, for example, in regularization terms or something like that?
Yeah, exactly. It would be also a very good thing to look at, because what I'm doing now, I'm trying to find the good slide. Yeah, so what I'm doing now is, so I take the output of the DRL, I directly inject them in the calculation of the controller gain, and that's only the calculation of the controller gain which ensures local stability, because we compute the gain K from this output of the DRL model so that the system is stable. And we guarantee that this can be done. So the values of the output of the DRL model are in the good boundaries, so that the gain K can be computed so that we have local stability. Sorry if it's not very clear, but for what you suggest, if I understood well, is to go a bit in reverse and to apply constraints directly on the output of the DRL model to fit the DRL controller, the model-based controller. Exactly. And to have stability, and definitely it's something that we could do. And for now, we didn't do it because it was not the easiest way, but it's definitely something that we should do, and also maybe find a Lyapunov function, or more like convincing like proofs for stability. Definitely.
Yeah, thank you for your answer. And another question, I'm wondering if you have performed some comparison concerning the computation cost of your algorithms, if that deteriorates with, for example, degrades with addition of this hybrid model, or it's better than only model-based. So.
Yeah, so what took the most time was the computation of the gain K, the recomputation each time step of the gain K. But in the end, as the DRL model was already trained, we had no significant differences of time step between the three compared controllers. So standard controller, adaptive without DRL, and adaptive with DRL. We had no differences because DRL was not making any difference. It was already trained. So time step was very, very, very fast.
Thank you very much.
No problem. Thank you for your questions.
Raphael?
Hi, yes, thank you for the presentation. Just a small question. I think at the beginning of the presentation, you said that you made the assumption for work for this PhD that there is only an sensors that can be faulty. So actuators fault, sorry. So how do you imagine combining this with the rest if there is faults with the software sensors and etc. How do you think your system could cope with it? I mean, is it something, because you make changes on the actuators, so is it something that can be combined with other fault detection systems, or is it something that should be generalized to all these kind of faults?
Yeah, thank you for the question. So we chose actuator fault because the principle of DRL is really to take actions according to an observation. So it was the most logical to use actuator faults and not, for example, sensor faults, because it needs to know its states. But we can definitely combine this actuator fault recovery with other types of fault detection and fault control. For example, we assume that there is no other disturbances, but we could definitely use a sensor to measure the current and add it to the controller independently of this control location process. And same for sensor fault, we can use also different kinds of fault detection and fault control for the sensor faults. And also, one thing that I'd like to do, and I didn't have time, is to add and to simulate the noises in the sensors to improve the efficiency of the transfer between sim and simulation and reality. So this is definitely something that we need to do. And yeah, the only challenge with this is that as we modify directly the model of the system, it's quite delicate to also overcome different kind of faults, because we don't want to adjust the model of the system if it's a sensor fault or if it's a marine current. So we need to be very careful about changing the model and to be sure that it's an actuator fault and not something else. This is why we just assume for my PhD that there is no other disturbances, so we can focus on this. But definitely, if we want to add other disturbances, we need to find other ways to include information about which type of fault it is.
Okay, thank you.
Martin?
Yes, thank you very much. Just in the continuity of the question that was just asked by Raphael, maybe this issue that Raphael raises might be be something you will want to see very much in detail when going from simulation to an actual real-world system, right? And if so, there is going to be two different kinds of disturbances, like synthetic disturbances, simulated disturbances that you already kind of project that there are going to be in your real-world environment. But this will never absolutely account for all of the real-world disturbances that you're going to find, right? So I think it was more like of a question of just highlighting what Raphael said of the importance of understanding maybe even in here there's a difference between synthetic and real-world disturbances.
Yeah, definitely, and I think we should perform online learning as well in the real world. For example, pre-train a DRL model on synthetic disturbances in simulation, and then continue training in real world to better adapt. But the problem with that is also the resource efficiency. So we need to have a powerful embedded system. But yeah, it would be definitely maybe a solution to continue the training.